So I want to start by asking us a weird question, and that is, okay, that's a kind of weird question, right? So what is it? Or before we do that, actually, let's just check one thing. I think we did this. Did we already do the Iris data set in Weka? I think we did it. Iris, the flower. Yeah, we did it, right? We did it, right? All right, let's just quickly review that one more time. So let's open up Weka. So go to Weka. And go to whichever version, doesn't matter, but I guess 3.7, if you have it on your computer. And go and use the Explorer version here, right? Use that. Everybody get that? Open? And open up the Iris data set. So go to File, Open File. And open up that Weka. You have to find it. Oh, it's in the, you have to go to Computer, Local Disk C, Program Files. Then you have to go to Weka and Data. Can everybody find it?
Yes.
And you go to the Iris one. And open that up. And over here, as I think I mentioned before, you have how many variables listed here? What's this? Sepal length, sepal width, petal length, and petal width, right? Those are aspects of a flower, right? Anybody know much about flowers? Okay, well anyway, the petal, the flower has petals, right? Petals, and they have obviously a length and a width. And there's also some other part of the flower called the sepal, and that also has a length and a width.
Maybe it's the one that's in the ground.
Oh, I don't know. I'm not sure what it is, but we can ask one of the biology teachers up on the third floor. But right now, yeah, you can also Google it. Okay, but also there's the class, right? Now, we talked about this before, right? What's the class mean? The class is over here. If you look here, it says Iris setosa, Iris versicolor, and Iris virginica, right? Everybody remember this? We did this already, right? Am I right or wrong?
Yes.
Yeah. Okay, so what's the goal of this problem? Later, do it later. What's the goal of this problem? When we do a data mining on this data set, what are we doing? We're trying to predict the class for a given flower. So I give you a flower that has a sepal length of 2, and a sepal width of 3, and a petal length of 3, and a petal, right? I give you some flower, and you can measure its first 4 variables for that flower, and then can you decide, is it an Iris setosa? Let's quickly take a look here. What do we mean, but what's the difference? Let's look at Iris setosa. Okay. So Iris setosa, maybe this is an Iris setosa, and there's another type called Iris virginica, and I don't know the difference between them, right? But the question is, can we predict what something is based on these values here? Do you remember this? Didn't we do this or not? We did it, right? Okay. So how did we do it? Anybody remember how we do it in Weka? I'll give you a clue. My mouse is pointing on it. Can you see it? Here. Can't you see it? I'll turn it on. It's not on? It should be on. Turn your screen on. Can you guys see it? You can see it, right? Your screen, you can see it, right? So you guys can't see it?
No,
Okay. So we're here. Well, how do we do it? It went off? Okay, so you click here, and then we are going to study today something called a neural network, which is one of the algorithms that we can use through Weka. And it's listed here, all of the algorithms, and here's a folder called functions. And inside there, you see one called multi-layer perceptron. Do you see that? And that's what we're going to study today. It's called multi-layer perceptron. It's also called a neural network. We're going to study how it works, the mathematics behind it. Okay? But anyway, let's just run it very quickly here and see what it does. Now here, one thing that I hope we talked about last time was this option here, percentage split. Can somebody explain to me what the purpose of the percentage split is about, or what that's about? Somebody explain that?
Percentage between the training set and the testing set.
Okay, right. He said something about training set and testing set. What does he mean? What's he talking about? We split the data into two sets. And the first set we call the training set. That's where we build the model. Then we want to test the model. So we have a separate part of the data, which we call the testing set, and we can test it on that data, right? That's the idea, right? Okay, so we'll use a 66% split. There's no rule about how many you should use. Let's just do that and check it, and it's so quick. And we find out, if we look at the results, that the accuracy is 98%, which is so super high, right? That means that we took 51 test records here. 51, it says 50 and 1. Okay, we took 51 test records. I hope you guys can, maybe you should move to a different computer, or I don't know. The whole lecture is going to be through that screen, and you won't understand any of it. Okay, better if you don't sit together. I'm sorry, but it might be better if you don't sit together. Okay, I'll give them a minute or two to start up. Are there any computers that are already on? No. Okay, let's take a quick break here. All right, while they're logging on, let's ask this question. Okay, so give me some answers to this question, which is this question here. What is science? So, can you guys help me? What would you say science is? What's the meaning of science? What does it mean? I'd like some opinions. Okay. No, you don't need to use your mouse to give me an opinion. I want your idea about what science is. Huh? In general. That's a very general question, right? What is science? I'm asking it because it might help us to understand what we're going to do today. It might give us a kind of a framework. Okay, so that was really good. What did she say? From observations. Say it again. Looking for a pattern, and then theory. I think that was almost perfect. Anybody else want to say what else science is? Does that sound right? She said you look at observations, you look for patterns, and then you come up with a theory. Now, what does a theory mean, by the way? And it doesn't have to just be like math or physics type science, but even something like political science, or something like, some other, where you do some kind of analysis, right? That's kind of fit into the same game. So what do you mean by theory? Hmm?
A systematic
Systematic study.
has some structure.
Has some structure. How about like accounting? Is that a theory? Maybe.
I think so.
It's a
Yeah.
language or method.
Would you, well, how about language itself, like learning French? That has a structure. Would you say there's a theory there?
Depends on knowledge.
For the language itself, I think there's a
Do you think there is in the language? But when you study French, do you learn the theory, or do you just
I
learn?
think not for learning French, but for
Uh-huh.
the language study, like
Can you give me an example?
like for example, what the word for example, the word is Spanish.
What?
For example, if you want to check the origin of one specific
Origin of a word. Okay, but so you, is that a science exactly? So you say, okay, what's the origin of the word agriculture or something like that, right? Something, and you say, oh, I think that comes from Latin or something, and blah blah blah.
Greek English.
What?
Like you check the origin of the word.
Right. I don't know if I call that science or not, but maybe it is. But isn't there something kind of more scientific than that? I mean, I think so theory, what does a theory mean?
It's like
What do we mean by theory? I don't have exactly a great answer
a good
myself.
hypothesis.
What?
A good
A
hypothesis.
good, okay, well, what is a hypothesis?
Like kind of like
Okay, give me an example of hypothesis.
tomorrow it will rain outside.
Oh, tomorrow will rain. That's a prediction, right? That's a prediction. Some butterfly? Or some animal. Okay, yeah. So if it rains, then some animal will fly somewhere or do something, right? Yeah, that's kind of a theory, isn't it? So it's a kind of like and it's kind of, theory is a kind of like related to predictions, right? Like that's kind of a prediction actually. You say, because you say, oh, it's raining, therefore I can predict that blah, blah, blah will happen, right? Something like that. Okay. Now, how about if I look at this, this video, one of these videos here, for example, this one was quite funny. How do I get that to work? Maybe if I do this, and click on it. This is quite funny, actually. Let's see, can I get the sound? Okay. Oh, but there's this horrible music in it. You probably like it. Oh no, this is not the right one. I want a different one. Which one had that? Oh, here. Maybe this is it. Yeah. You know what he's doing? You know this experiment? You know, he's trying to understand the gravity, right? And we say that distance equals 9.8 meters per second squared t, right? Have you seen that before? In basic physics class? In other words, what am I talking about here? If you stand on top of a building, you take a tennis ball and you drop it, you're asking how far, what's the distance it will fall given a certain time. So this tells me that after 1 second, it's going to fall what? What's the calculation after 1 second? 1 times 9.8. right? So this tells me that after 1 second, we'll have fallen 9.8 meters. Okay, and after 2 seconds, how far will it have fallen according to this equation? So it's 2 squared, which is 4, times 9.8, which is almost 4 times 10, so it's almost 40. Right? Almost 40. So after 2 seconds, it will have fallen to about 40. And after 3 seconds, it will fall to what? 9 times 10, say. So that's 90, right? Okay, so we have this, right? This is kind of a theory, right? Now let's just look at it. So this is, what this is trying to do is, those dots are supposed to be after 1 second, 2 seconds, or after the same amount of time. So what should happen is that the first dot should be closer, and then they get further and further away because it's falling faster and faster, so in the same time, it drops further. It doesn't quite look like that, but that's the idea, right? It should drop further later than at the beginning, right? So if you're taking a picture, for example, every 1/10 of a second, then in the first few pictures, the distance should not be far, but afterwards the distance, so that's what they're trying to show here. Let's see it. See, they have these measures there. Why isn't it working now? Okay, here. Now they do a higher distance. I don't know why the music doesn't come, but it's this hip-hop Kanye West music, so I'm glad it's not there. Funny, these guys are sitting there doing this. But you can sort of see how it's spread out more and more and more and more? You see that? Now they do that. See how it's spread out more and more and more and more? So where did this rule come from? Well, it probably came from doing some kind of... Oh, this is the funny one. So you see even there, spreading out more and more, right? All right, so where did this come from? Well, maybe, Galileo, a long time ago, did some kind of similar, I don't think he jumped off a thing, and he didn't have a camera exactly, but something like this, right? Okay, everyone understand? Okay, all right, anyway, so, all right, now, let me ask you, the reason I ask you, so what is science, is if I actually take a tennis ball, or maybe it's not even a tennis ball, like a trash can lid, and I drop it, is it going to follow exactly this equation? Not exactly, right? Okay, it won't follow it exactly. There's going to be some difference. Why? Why? Sort of depends on where you are, yeah, could be. What do you mean by that? I don't think it depends on that exactly. Oh, slightly it could, but not really that. But maybe if you're really, really, really high, it could be very slightly different than that. But yeah, okay. And what else?
I guess the friction.
Yeah, right. The air friction definitely is a factor, right? The air friction. Right, so if you drop a tennis ball versus a trash can has a lot of friction, right? So it's just not it's going to be different than a tennis ball. Now, Galileo did say he dropped like a heavy object and a light object, and they both did approximately the same, but the size of the two objects was basically the same. So the friction was basically the same. So it's not the weight that affects this actually, but it can be the shape, because the shape creates more friction, can create more friction, so it could be different. So it's not going to be exactly this, right? So if it was exactly this, then this curve, if I put it t here, and d here, this curve would be, as time increased, the distance would increase, right? Distance would get more, and it would get more as t squared grows. It would grow as t squared grows, right? In other words, it's going to be a parabola shape, right? That doesn't, we're not saying the ball is falling in a parabola shape, just saying the relationship between these two variables is parabolic shape, right? So it's going to look like this. If it was exactly that formula, right? We just said that it's not going to be exactly that formula, right? It's going to be a little bit off, right? So if we actually measure it one time and another time and another time and another time, I doubt that the distance is actually going to be exactly right there, and exactly right there, and exactly right there, right? So it might be like this, right? Here, and here, well, and maybe here, and maybe here. I don't know, right? I'm just making it up, but it could look something like that, right? It's not going to be perfect. Now, the question is, should you say, if you just look at this data, should you say that the relationship between t and d is like that? Or I guess I should say like this. Like that? Or like the green line? Which should you say, right? And that's the question, right? And we don't, how do we answer? I mean, what does that mean? What do I mean by asking that question? Like, I mean, this is the actual data, right? Right? We got this, at 0 it was 0, here it was here, here it was here, here it was here. So should I say that it follows this pattern? Or should I say that it follows the green line? Well, I had a physics professor when I was your age. And he was a great professor. He was like wild guy, but wonderful guy. And he was like a really crazy thinker. And he used to say that scientists are paranoid because they see things that aren't there, or that may not be there. And he meant that in terms of this picture. So the scientist is going to say, oh, I think that there's a real relationship between this, which is the green line, but all we can observe is the red stuff, or the blue stuff, right? So we're imposing like our own theory on reality, right? And that's kind of what science does, right? Right? It says, I think that it's this green, even though all we can see is the blue or the red. Right? So kind of paranoid thinking in a way. Right? Kind of interesting way to explain it, but he said, kind of paranoid. We're seeing things that sort of aren't there. Right? So that's a very interesting thing to say. Okay, so does everyone understand what I'm talking about? More or less?
John Nash.
What?
How about like people like John Nash?
No, I don't mean people like John Nash. But I mean, by the way, I had a professor that used to work with him.
Wow.
Yeah. I had a great, brilliant professor, really great mathematician. And he used to work with John Nash and also Paul Erdos, who was like even more kind of greater mathematician than John Nash. You should, if you can ever read something, it's so entertaining about Paul Erdos. I went to a conference actually about Paul Erdos. He was there, and if you can ever read this, it's called The Man. I think it's called The Man Who Loved Numbers. You can easily find it on the internet. The Man Who, it's just incredibly funny. He was so amazing and such a strange guy. Anyway, Paul Erdos. Anyway, so yeah, but I don't mean like John Nash. I mean, no. This is what a normal scientist does, right? They impose some kind of reality here, right? But the question is, I mean, impose something on reality. So the question is, though, if we have the data, do we say, now, if we only had this red, could we make future predictions? Kind of hard. What would you predict for the next one? Well, who knows, right? It's kind of hard, right? Yeah. You could kind of look for it, and there are some, but this is clear, right? We have a relation. Anyway, maybe not. But okay, so does everyone get what I'm trying to say? Okay, so that's gonna help you later when we talk a little bit more. But today, we're going to study neural networks. And they're also called artificial neural networks, or multi-layer perceptrons. And they're abstracted from biological activity in the brain. And we have this terminology. We have input variables and output variables. So in the Weka example that we just did, how many input variables did we have? No, the input variables were 4, and the output variable was 1. What was the output variable? It was whether it was a Setosa, Virginica, or the other thing. I forget the other one. And what were the input variables? So that was one variable, the class of the flower. And what were the input variables? There were 2 lengths and 2 widths. Petal length and petal width, sepal length and sepal width. Okay, so how many input variables were there? 4. And how many output variables were there? 1. Okay, now other words for input are explanatory variables or predictors. And other words for output variable is the response variable. Okay? And actually, I want to take this back. It's not always categorical. And the thing about about neural networks is that they are nonlinear. Now, if we just had this data here, these 3 blue points, we could try to fit a straight line between them. So we should say maybe like this line. I don't know, I just drew that line, but you can't even see it, right? But that line, right? So we could try and fit a straight line model on that. Okay? And maybe that's what we could do. Maybe that's what we would do. Now, we didn't try and fit a straight line model. We might have tried to fit a parabolic model on it. Okay, line or model, curve or model. It's the same thing in this case. Okay, so we could try and fit a straight line model, but the thing about straight line models is that they're not obviously not that flexible. Right? They can't capture as much of the data as a curved line model can. So neural networks, now this model we say has like basically order 2 because it has a square in it. And an order 3, so an order 2 model we know is a parabola. An order 3 model can be like that. An order 4 model, like if this was to the 4th power, we could get, I think, something like that. So the higher that order, the more curves you can get, the more flexibility it has in terms of trying to fit data. Does that make sense?
What's higher order?
Higher order means this.
Okay.
4, 5, 6, 7. That's what I mean by higher order. Okay? So the higher order, the more curviness you can have in it, means the more flexible you can be in terms of fitting the data. It's also a more complicated model, though. So you pay for the flexibility with complexity. Okay? So that's the trade-off. Okay? Now, the thing about neural networks is they're extremely flexible. They're so flexible that you don't want to use the entire flexibility of them. Because what happens is you could get it to look like the red thing, which you don't want to do, because then you're kind of ignoring the science. Right? You're saying, I don't believe there's any real relationship. I just connecting the dots, and there's no, I don't have like any real theory behind it. Okay, here, when we go to the green, we're saying there's a kind of theory, and we're saying, oh, okay, there is a theory, and we're just saying there's some kind of error off of that theory, like because of other factors of which we can't account for. But there is a kind of true relationship between T and D. Okay? But if you just go to the red, you're sort of saying, no, there's really no true relationship. It's just the dots, and that's all. Okay? Do you understand what I'm saying? Okay? So when you do a neural network, and other techniques as well, you lose kind of the science if you're not careful. Okay? So you don't want to do that. So we'll see what that means later. Okay, now where does the neural network theory come from? Somebody, was studying neurons in the brain, and they decided to come up with a kind of artificial model of that, and see if they couldn't use it to work with data. Okay, so I don't know much about biology, but these are like something happens over here, and then it gets translated through this circuit and ends up doing something over here. Okay, that's the basic idea of a neuron in our brains. Okay, so I don't know how it works. I'm not a doctor. But when we make an artificial neural network, it looks like this. So what we're going to do is we're going to put values for different variables over here, and then we're going to predict something over here. Right? So what what's the example we just used? For the iris, right? We put in, let's say, we put in the sepal length, sepal width, petal length, and petal width. So this flower has a sepal length of 1.3 and a sepal width, sepal width of 0.9 and a petal length of 2.2 and a petal width of 1.8. So we put those in, and we get a prediction. Oh, this is Iris setosa. No, this is Iris virginica. No, this is, right? We put in a particular set of values into the model that we built. We used Weka to build the model. Then we take a new flower, we put it in, and we get a prediction for what that is. You understand what I'm talking about or not? Is that clear? Okay? So that's what this picture is. So what's x1, x2, xn stand for? The input values, right? Right? What other words do we use besides input values? We used explanatory variable. What else?
Feature.
Huh?
Feature.
Features, attributes. What else? But those are actually features and attributes don't necessarily mean input ones. They're just in general. Could be either way. But explanatory variable. Did we say anything else? Predictors. Predictors. So these are the predictors. These are. And we put it in the machine. Here's the machine. We perform the prediction. Turn it out. And it says, oh, it's an Iris virginica. Okay, you understand? Or no, it's an Iris setosa. Right now, it's not necessarily right, but we saw that how accurate was the Weka predictor? 98% accurate. It's pretty good. Okay, but usually you don't get that kind of accuracy. But okay, so does everyone understand this? The left side of the picture and the right side of the picture? The x side and the y side? Okay, and then inside is the way the neural network works, and that's what we're going to study today. Okay? You understand the picture? Okay, so the inputs, x sub I, are collected from upstream neurons, or the data set. So not, in this case, not upstream neurons. The inputs are collected from where? From the data set, right? Here, the data set. And combined through a combination function, so that's what happens in here somehow, that's what we're going to study today. So somehow we do the Weka thing, such as a summation function or something. which is then input into usually a nonlinear activation function. Okay, that's not clear at all right now. Anyway, that's all what's happening inside to produce an output response Y, which is then channeled to, so that's enough for that slide. Okay, here's an example, not the Iris data set, a different example. So what does it say? What's the tiny example on what? What does it say? Tiny example on what? Up at the top. What does it read? Read that? Here. What's it say? Oops. Let me do this. Fix this pointer. Arrow options. Visible. What's this say? Tiny example on tasting scores for what? 6 consumers and 2 predictors. Actually, I think that's a mistake. I think it's 6 cheeses and 2 predictors. So I think let's say 6, not 6 different consumers, but on 6 different cheeses. So look at the first row. What do you see? Well, look at the column headings first. What do we have in the first here? This is the observation. So you have observation 1, 2, 3. In other words, let's say this is cheese 1. And then what do we have? We have an information about what? About cheese 1. How much fat it has in there. Okay, and then we have what else about cheese 1? How much salt is in there. And then whether people liked it. And a lot of people don't like cheese, right? Right? A lot of people don't like cheese. Yeah, it's true. My wife doesn't like cheese too much. It depends on the cheese. So if I give her blue cheese, she'll throw me out. And in Japan, they have what? What's it called? No, I mean the beans. Not cheese. Natto. And a lot of people in Japan don't like natto, but a lot of people do like it.
I love it.
Okay, so you love it. So, okay, but maybe there's different types depending on what you might not like, all right? So that's the idea here. There are different cheeses, right? So depending on the fat and the salt, they're going to say 1 or 0 for acceptance. Okay, 1 I guess means what? That they liked it, and are acceptable, and 0 means that it's not acceptable, okay? Okay, so we have how many cheeses here, or how many observations? I think there's a mistake, because you can't have different fat scores and different salt scores for the same cheese. So it must be different cheeses, not different people. It says different people, but it has to be different cheeses. Okay, so how many cheeses are we testing here? 6, right? How many predictors do we have? How many explanatory variables do we have? 2, right? Okay, 2 explanatory variables. And what's the class? The class means what are we trying to predict? Acceptance or not, right? What was the class in this problem, the iris? The class was the type of flower, right? And how many different values could that type of flower have? 3, right? What were they? Iris setosa, Iris virginica. What was the other one? I always forget it. Anyway, there was one more. 3 different types of flowers. But in this case, what's the class variable? What are we trying to predict here? Acceptance or not. So how many values can that be? Just 0 or 1, right? Either it's acceptable or it's not. Okay? So, depending on what the problem is, you could have many different values in the class. You could have just 2. You could have 3, because you're talking about different, irises. Or you could have different beers. You could have 10 different beers, and you want to predict whether someone's going to like this beer or this beer or this beer. So you could have lots of different values, right? Understand? But in this case, how many do we have? Just 2. Okay, so 2 predictors. What are they? Fat and salt. And the question is, can we predict the rating, acceptable or not acceptable, based on the amount of fat and salt, right? So this is a very tiny data set. We're not going to get good results in terms of building a model with this kind of data. We need much bigger data set. In the iris data set, we had pretty big, not big, but we had 150 records. Here we only have 6. Okay? But just for example. And this is what we mean by a neural network. So we're going to study, this is what we're studying. And this is the way they're built, sort of. Okay? And those dots are called nodes. Okay? Everyone understand? Everyone say the word. What are they called? Nodes. N-O-D-E-S. Those are called nodes. How many nodes are there in this picture?
The points?
What?
The points?
Yeah, the dots, yeah. How many are there? 10, right? 10. And the green dots here are called the input layer. And the purple dots are called the hidden layer. And the red dot is called the output layer. Okay, so in neural networks we have 3 layers. Although sometimes you can skip the hidden layer, but that's not a very interesting neural network usually. And you can have, in the hidden layer, you can have several columns of dots. But we're not going to study that because it just gets more complicated. But when you run Weka, it can have many, many columns. Anyway, it doesn't matter. Don't worry about that right now. This is a neural network. Now, what goes in here actually are the value, the input variables. How many input variables do we have in this problem? 4. How about in the cheese problem? Salt and fat. So how many in the cheese problem? 2. How many in this one? 4. The input layer is usually exactly the number of input variables. So if we were doing this one, we'd need how many? 4, because we have 4. 1, 2, 3, 4. If we did the cheese one, we only need 2 green dots, generally speaking. Okay? Okay, here's an example. Here's the example with the cheese. So 2 predictors, fat and salt. Can we predict the rating, acceptable or not acceptable, based on the amount of fat and salt? And this is what the neural network could look like. So what are the 2 nodes in the input layer labeled as? They're labeled as 1 and 2. And what do they accept? The fat and the salt reading. So what we're going to do is we're going to take the first cheese and we're going to find out how much fat and how much salt is in it. And we're going to put those into node 1 and node 2. Okay? Okay? You'll see what we do. And then this is called a graph in mathematics. Not this. It's different than this kind of graph. This is obviously called a graph too, but it's a different kind of graph. They have something called graph theory. And in graph theory, you have 2 things. You have points and edges. Or they call them vertices and edges. Or you can call them nodes and edges. And that's what this consists of, right? What do you see in this graph? You see nodes. How many nodes do you see here? How many? Total number of nodes. Total number of circles. 6, right? There are 6 nodes. And then these lines are, in graph theory, they're called edges. Okay? And not all edges have to have arrows on them. If they do, they're called directed. Doesn't matter, but that's just what they're called. So, anyway, how many edges or how many lines originate from node 1? 3, right? And what are they labeled as? W13, W what? W14, and W15, right? They're labeled like that. And how many nodes originate from the node 2? 3, and what are they labeled as? W what? 23, W24, and W25. Can you see these? If I can see them, you must be able to see them because my eyes are really bad. Okay? Okay, one more. How many nodes originate from node 3? And what's it labeled as? W36. How many from node 4? 1. And what's it labeled as? W46. And how many from node 5? 1. And how many? What's it labeled as? W56, right? All right. Can you see how the nodes are, I'm sorry, how the edges are labeled? Why is this labeled W13? It goes from node 1 to where? To node 3, right? Why is this labeled W14? It goes from node 1 to node 4, right? Why is this labeled W15? Okay, so the labeling is obvious, right? Right? Okay, everyone see the labeling? Okay. So if you know if you have the name of the label, then you know where it's going from where to where, right? If I tell you I have a label W38, then you know what? It goes from node 3 to node 8, right? Of course, we don't have a node 8 here, but I'm just saying, right? If I told you I had a W38, you would know what? That it goes from node 3 to node 8. Okay? Everyone understand? Okay. That's the labeling. And we also have the thetas, and so on. Okay, now, so reading it from the bottom of the screen says, neural network for the tiny example. Circles represent nodes, and the W's on the arrows are the weights. Well, we don't know what the weights mean. And the theta sub I are the node biases. We don't know what that is either. The fact that there are 6 nodes and 6 consumers is not meaningful and just a coincidence. Okay, not 6 consumers. There were 6 cheeses, right? I said not consumers, right? We said there were 6 cheeses, and you might think, oh, maybe that's why there are 6 nodes here. But no, it's just a coincidence. It has nothing to do with anything. Okay? Any question so far? Okay. Now, nodes 1 and 2 belong to what's called the input layer. Nodes 3 to 5 belong to the hidden layer, and node 6 belongs to the output layer. The values on the connecting arrows are called weights, and the weight on the arrow from node I to node J is denoted, that should be Wij, W sub ij. The additional bias nodes, denoted by theta sub j, serve as an intercept. We'll talk about that later. These are all explained later. Okay. Computing output of nodes. So here's what's supposed to happen. We have something node, 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 node. And then maybe here, something like that. Isn't that what we had? Something like that? Right? We had a picture like that. So what's going to happen is we're going to put some values in here. For example, what was the first cheese? What was its fat and salt score? Can you see that down at the bottom? What was the fat score? 0.2, and the salt score was 0.9, right? So we're going to put 0.2 goes in here, and 0.9 goes in there. Okay? Then what it's going to do, and then there are going to be these weights, right? We said there are these weights, W's, right? On here. Weight, weight, and so on, right? The different weights. What happens is, this 2 gets multiplied by this weight and gets sent to this node here. And this, 0.2 gets multiplied by this weight and gets sent to here. And this 0.2, and the 0.2 here gets multiplied by this weight and gets sent there. Do you understand the calculation? Okay? And then, so how many values are being sent to, what's this node? 1, 2, 3. How many values are getting sent to node 3? This one and this one, right? So how, it's going to be, what did I say? Let's call, what do I call this node? I'm sorry, what do I call this weight? W sub what? 1, comma, goes from 1 to 3. So we call it W1, comma, 3, right? And what do I call this one here? From here to there, what's that called? W2, comma 3, right? And, okay? And this value is called x1, and this value is called x2. Okay? So what is x1 equal to? 0.2, and what is x2 equal to? 0.9, and W1 is going to be, W13 is going to be a weight, and what was this one? W23 is a weight. What's going to happen is, like I said, 0.2 times this, and 0.9 times what? Times this one, right? Let me write that down. 0.2 times what? W13. And then what was the other calculation we're going to do for this? 0.9 times what? W23. Right? W23. And what we do is we add those up. So in other words, I take this value times this weight plus this value times this weight, and that's what goes here. Is this clear or not? All right, let's look at, okay. So the output of these nodes, 1 and 2, will be, oh sorry, never mind that. So now we want to compute the outputs that go into node 3, node 4, and node 5. So can you write down on a piece of paper what you think, just for practice, is going to be what's going to go into node 3? Just to get your hands working. What is going to go into node 3? Write it down yourself. And you can use these values. The first cheese here. Or if you want to call them x1 and x2, that's fine. Use those values for x1 and x2 if you want, 0.2 and 0.9. And I want to figure out what is supposed to go into node 3, what's going to be sent to node 3. Somebody want to write the answer up on the board? Anybody want to do it? So the question is, what goes into node 3? Node 3, what goes in there? Okay, good. Good. I think that's right. That looks right. Does everybody agree with what he wrote? So the fat, or we also call it, I mean, what was the actual fat? 0.2. Could write 0.2 times that. And the salt was what? 0.9. You could write it that way. Or if you want to call this x1 and x2, that's also okay. Okay? Any of those is fine. Is that clear? Everybody get that? All right, so then you can also figure out what goes into node 4, right? And also what goes into node 5. Okay, do you get it? Okay. So next we want to input their outputs. That is, we want to take the fat and the salt and put them into node 3, 4, and 5. What will be input into these? The hidden layer, 3, 4, and 5. So here I'm just explaining about the subscripts, which we already looked at. So why do we call this 2, 4? Because it comes from 2 and goes to 4. So we call it that. So I'm just explaining that. So I, if we write it as I and J, I means what? Where it's coming from. And J means what? Where it's going to. Okay, so I means again, where it's what? Where it's originating, and J means where it's going. Okay, everyone get that? So same thing here, right? How about this one? W46, why? Because it's originating from where? 4 and going to 6, right? Okay, so I'm still explaining that again. Okay, now here it is. Now this looks kind of awful, but you just did this actually. It's not as awful as it looks because you just did it. He just wrote exactly that when he wrote this. Okay, well, with one addition, but basically that's all. Why? Because this is plus, right? Instead of plus, we could use what symbol? Sigma, right? Right, sigma. Does everybody know sigma or not? Should I review sigma? It's not a math class, so maybe you don't remember it. So let's quickly review it. If I write sigma 5 times I goes from 1 to 3. What does that mean? What does that mean? So that means first you put I equals 1 into this formula. Then you put I equals 2, then you put I equals 3. So if I put I equals 1 into this formula, well, I obviously get 5 times 1. If I put I equals 2 into this formula, I obviously get what? 5 times 2. If I put I equals 3 into this formula, I obviously get what? 5 times 3, right? Okay, so that's what I mean. And then, what's the sigma tell me to do? It means to put a plus in between each one of these. So put a plus and a plus. So that's what this means, right? Let me repeat that one more time. If I write this, I'll write all that. It means just replace I by each value from here to here. So if I replace I by 1, I get what? 5 times 1. If I replace I by 2, I get what? 5 times 2. If I replace I by 3, I get what? 5 times 3. And then what's the sigma mean? It means for each of those terms, just add them all up. Okay? How about if I wrote that? Now what? Again, replace I by 1, I get that. 5 times 1 squared. Replace I by 2, I'd get what? 5 times 2 squared. Replace I by that, I'd get that, right? Is this clear? Everybody know the sigma notation? Let me try one more. How about this? What's that mean? So it means just replace I by what? By 3, then by 4, then by 5, then by 6. Let me say that again. Replace I by what? By 3, then replace I by what? 4, then replace I by what? 5, then replace I by 6. You understand? So if I replace I by 3, what do I get? Replace I by 3, what do I get? 3 plus 5, right? Squared, right? So let's just write that. You don't have to do the calculation. 3 plus 5 squared, right? I replaced I by 3. Now I replace I by the next number after 3, which is what? 4. So I get what? 4 plus 5 squared, right? Now I replace I by what? The next number after 4 is 5. Right? I'm doing I, the integer values 3, 4, 5, 6, because I stop at 6. Okay, if this was 60, then I'd have to go 3, 4, 5, 6, 7, 8, 9, all the way up to 60. But I didn't make it that hard to write, I just made it 6. Okay, so first I put in I equals 3, then I put in I equals 4, then 5, then 6, and then I can stop. Right, because it says stop at 6, right? Everyone understand? So I get 3 plus 5, 4 plus 5, 5 plus 5, 6 plus 5. 5 plus 5, and 6 plus 5. Squaring all. And then the sigma tells me that what I'm supposed to do is add these. By the way, there is some math where you write something like this. What's the difference between the two? This one and this one. Instead of adding, you multiply. Pi stands for product. Okay? So sometimes in math they do that. We don't usually do that in basic math. Sometimes we write that simple also. That would mean instead of adding these, you would multiply. And how about this, by the way? What's that mean? So this was a specific function, I plus 5 squared, right? But now I'm talking about a general function. But still, what do? You just put I equals 9, 10, 11, 12, and add. So that means what? F of 9 plus F of 10 plus F of 11 plus F of 12. That's what that means. That's what this means. Okay, is this clear? No? Is it clear? Some of you have a lot of math training. Some of you don't have so much. So I want to make sure, we have a very small class, so I want to make sure everybody follows along with everything. Okay, is this clear? Okay, sigma notation, it's useful. Okay, so going back to this, what did he say goes into node 3? The fat times this weight, and the salt times this weight. Now I see a plus there, so maybe I can use a sigma here. I see a plus, so maybe I can use a sigma. So how about if I write it like this? Sigma, what was another thing for, instead of fat and salt, we could use what? X1 and X2, right? Okay. By the way, when I did this one, this was for this, right? How many terms were there here? Right? And that's why, because I went from 9, 10, 11, 12, right? So that the number of i's that we use gives us the number of terms, right? Right? The number of i's gives us the number of terms, right? So here, how many i's were there? 9, 10, 11, 12. That's 4 i's, that's why we got 4 terms here, right? Each time we put in a different I, we get a different term. So if we're going to have a sigma here, how many terms do we want? There's only 2 terms. So we want I to only generate 2 terms. So maybe it will be I equals 1 to 2. That's all in this case. Okay, so what would it be? Xi, and this is a little complicated, W something. What is it? W13, W23. Something's wrong. Yeah, it works. Sorry. So 3 is the same, right? 3 doesn't change. So I'll put the comma 3 there. And what goes here? I. Does this really generate? What I want to generate is this. x1, w13 plus x2, w23. Isn't that what I want to generate? Right? And I think this will do it. Let's check it. Let's check this. What does that give me? What do I have to do? Put I equals 1, see what I get? And then I equals 2, see what I get? And then add them. Right, so let's try it. I equals 1, what do I get? x1 times w, that's an I. So w what? 1 comma 3. Okay, I did it when I equals 1. Now do it when I equals what? 2. So what do I get now? x2 times w what? 2 comma 3. And then the sigma tells me to put what in between them? A plus sign. So doesn't this generate this? In other words, doesn't this generate this? Okay? So that represents what we're feeding into node 3. Right? That's what we did, I think. Node 3, yeah. That represents what we're feeding into node 3. Do you understand? And how about if we want to know what we're going to feed into node 4? Ugh. What's that? I think this 3 will change to 4, right? Because this was what? This was 1 to 3. That's here. One to 3 and 2 to 3. Now we want to go here. So it's 1 to 4 and 2 to 4. So yeah. So I want to have what? X, I, W, I, 4 will do it. Sorry. That will do it. Okay, that's going to tell you what's going to go into node 4, right? Okay? Right? And understand or not? This is just a convenient way of writing what I hope you already understand. Is this clear or not? I see not so clear faces. If you don't understand it, it's kind of stupid to go forward. Let's see. Okay, what is this notation, by the way? It says I equals 1 to p. That makes it more complicated. Okay, why? But what's our p in our case? How many? This means we're going, what did we say? We're going from 1 to what? Just from 1 to 2. So p is just 2. But they're just being more general there because we might have more than just fat and salt as predictors. In our case, we have how many predictors? Just fat and salt. So we only have p equals 2 predictors. Okay, but we could have more, right? Like in the Iris case, we had 4 predictors. So then we'd have to do 4. There'd be 4 of these nodes here, there'd be 4 of these nodes. So we'd have to do, we'd say how many calculations do we have to do to figure out what's going into node 3? How many calculations? We'd have to do 4 calculations, right? We'd have to say what's coming from node 1, what's coming from node 2, what's coming from node 3, and what's coming from node 4 into this node, right? Is that clear? Okay. All right. So I said, so in our case, p is just 2, right? And since j and j, since it is the downstream, will be either, so what will it be? By the way, what do we mean by upstream and downstream? So if you're swimming in a river, and the river is going this way, right? Then if you're over here, do you say, are you downstream or up? No, I got confused. Are you downstream or upstream? I think here here you're upstream, and here you're downstream. Okay, so upstream, so upstream comes first, right? So these are called upstream, and this is called downstream, right? Okay. So J is for the downstream, so these, right? So this is for where we're going, and this is from where we're coming from, right? So that's called, where we're coming from is called what? Upstream, right? And where we're going to is called what? Downstream. No. Yes. Okay. All right? All right, let's go on. Oops. So we do this calculation, and then, unfortunately, we have to take that whole result, that is this whole thing here. Forget about this for the moment. Just ignore that. Not even, it's really, it's the least important part, and we can just ignore it. Actually, because it could be 0. So just ignore it for now. Okay, so let's say it was equal to 0. So we only have this. That's what we've been talking about so far, right? Everyone agree that this is what we've been talking about? This is going to calculate what goes into what node, by the way. See if you understand this notation. This is going to calculate what's going into which node. What? The jth node. Right? This weight goes from where to where? From I to j. What's changing in this? Is j changing here? No, what's changing here? I is the thing that's changing. So I will be 1, I will be 2, I will be 3, but j is always the same. So it's always going to the jth node, but it's coming from the different i's. Right? Is that clear? Okay? So, anyway, we have this. And this is going to tell us what's going into the jth node, like this node or this node or this node. Unfortunately, that's not the end of the story. It's more complicated than that. Okay? After we go through all the calculations for this, and note that this is just for a single j, meaning a single downstream node, then we have to put this result into another function. So we're going to take this and put it into a function. Now remember that this turns out just to be a number, right? Right? This is just a number, right? After we go through all the calculations, it's going to be some number, like 5, right? Because we're going to put, 0.2 and 0.3 into here and here. Then we're going to multiply the 0.2 times something and the 0.9 times something and add them, and we're going to get some number in here, right? It's going to be a number. And then we're going to take that number, we have to put it into another function. Okay, now I know it's complicated, but you decided to take this class. Now this is probably the most complicated, or one of 3 of the most complicated stories that we have to present. Okay, so this neural network is definitely not simple. And there's another, the tree diagram 1 is not that simple, and the naive Bayes one is also not that simple. So those 3 lectures are pretty complicated, and this is one of those. But anyway, so I just said, so we're going to take this, and we're going to get a number in here. We're going to get a number as an input in here, right? And then we're going to take that number, we have to put it into one more function. Okay, so that's what I said. Then we have to put this result into another function. So we have to take all that mess and put it into another function, which we'll call g. Okay? And then we'll be done with our big calculations. Okay? But we do have to do that. So what kind of function does this have to be? G can be any function. So what I mean by that is you can try this for lots of different functions, and maybe some of them will predict well, and some of them won't predict so well for your particular data set and so on. So there's no rule about what function it should be. You're just hoping that whatever function you find is going to end up doing good predictions. That's all. That's the criteria. So it could be any function except as long as it's either always increasing or always decreasing. Increasing means that as its height, that its height increases as you go from left to right. Now that's wrong. It should say, I'm sorry. Anyway, is this function increasing or decreasing? It's obviously decreasing, right? I should have given an explanation for decreasing with this picture, but anyway. Okay, so this is a decreasing function. So this kind of function would be okay. Remember, I'm describing this g function that we're going to put our calculation into. Okay? So I can use any kind of g function as long as it's either like this, it's always decreasing, or it's like that, always increasing. Any function like that is okay. So there's so many different functions you could come up with, like that. But how about this function? Could I use this function? No, because that's not always increasing and it's not always decreasing. It goes up and goes down. That kind of function we can't use for g. Okay, now I know this is very complicated and you say, what the hell is going on here? But I'm trying to present it anyway so that you can say that you learned about neural networks. Now, to be honest, once you get the basic idea of this, unless you want to work on creating a new type of neural network for some particular problem, which you could probably do, but in general, you're not going to have to do that at all. You're working for a company, unless you're like a programmer that has a specific problem that you're trying to solve, like I want to predict how many cars, these kind of people are going to buy. Maybe you'll develop a specific kind of neural network and you'll have to think about all this. But other than that, you never need to think of it again. But you can say, oh, I have the basic idea of what a neural network is if you go through this. Once you know what it is, then we just go to Weka and you just do that iris thing and you never even think about what it was, where it came from. But I am trying to explain to you where it comes from. So you don't have to sweat it, but it's nice to have a feeling for where it comes from. And if we get to the end of this lecture, you will have a feeling for where it comes from, or how Weka does its job of making the predictions. Okay? Anyway, going back to this. We take that calculation and we have to put it in a g, and I'm just trying to explain what g can be. So I just said as long as it's decreasing or increasing, it's okay, but this is not okay. Okay? Okay, so that leaves us lots of kinds of g's that we could use. Now that's what I'm saying. If you're a programmer and you have to figure out, okay, how many cars is the people in Beppu going to buy, and you're trying to predict, blah, 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 you might try lots of different g's. Now I've never done anything like that in my life, but you might try and figure out, so look at different g's and see how well they predict. And you come up with different math functions for g, and I don't know, you could do it. Okay? So g can be what's called any monotonic function. A monotonic function is just the word they use in math for something that's either always increasing or always decreasing. It's a one-way function. Okay, it's always going up or always going down, but not going up and down, called monotonic. So if you want to sound fancy, my phone is going off. What's that? Okay. If you want to sound fancy, you can talk about monotonic functions. If you don't care, don't do it. Okay. Now, the typical examples of g are linear functions, exponential functions, and logistic functions. Now, I doubt that anybody has worked with logistic functions. Let me see. Has anybody worked with logistic functions? Okay, one person, only one person. That's typically nobody has. So you don't know what a logistic function is. But you do know what this is, right? Linear function is just this kind of function. That's linear, and that's linear. So you certainly work with those. Now, exponential, I think you have worked with exponential functions. What is an exponential function? It's like this, right? You've worked with that. Maybe you don't remember it that well. but you've worked with it. What's the difference between this function and this function? What's the difference between those two? The exponent, the variable is where here. It's in the bottom, right? In the base. Where is it here? It's in the exponent, right? Right? The variable is up here in this one, but it's not up there. Is there a difference between these kinds of functions? Big, 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 big difference. Exponential functions grow much, 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 much more quickly than this kind of function does. So much more. It doesn't even make sense. Okay? But they are both increasing functions, at least when x is positive. Right? What's this function look like when x is positive? Looks like that, right? Parabola. Right? That's increasing when x is positive. Exponential function looks like this. That's always increasing, even when x is negative. So it's still an increasing function. We said that what kinds of functions can we use? They have to be increasing functions. So these are all okay. And then there's one more, and then we'll take a quick break. There's one more, and that's this kind of function. Is this an increasing function? Is it always increasing? Yes. Right? And some people call it an S curve, looks like an S, but this is an example of what's called a logistic curve. Okay, it has a certain equation for it, and it's very popular in these days. People use it for a lot of stuff. It can be in social science, it can be in everywhere. People use it, and it looks like that, looks like an S. It's also called a sigmoid curve. Okay? Okay, so those are the kinds of choices that we have. Now I talk a little bit about why people use logistic curves. But what time is it now?
38.
We only have 12 minutes, right? Okay, let's take a 2-minute break and then finish with 10 more minutes. So we'll have to continue with neural networks next time, which we'll do. But, okay, let's take a 2-minute break.
You just push the button and it says you want to sleep direction when you don't actually.
You can check. You can just check. When you didn't sleep. Can you play the deep sleep?
Really? I mean, like, it's not like you don't have to do anything at the time.
No. Didn't you push the button when you start sleeping?
Dude, like, sometimes I try to sleep, I can't sleep anyway. That won't work. Like, sometimes I try to sleep for like 30 minutes and then I can't sleep and I'm like, okay, let's watch a movie. I watch the movie and I'm like,
No,
oh, maybe I should sleep again.
No, it just counts. Like the data doesn't do anything else.
For the class.
So for this class, I just want to know about
But like, I would like to know that too, but like, for
so you
awake, you said sober.
It's over, right?
When
So these cars, these cars are so it's not nothing with the features. So like you know, it's one with red.
you made a prediction. You,
Okay, let's just spend another 10 minutes. So we said that we have to take that whole mess and put it into some g function. And we said, well, what g function should we use? And we said we could use a linear function, we could use an exponential function, or we could use that S curve, which was called a sigmoid function, or a logistic curve. And that's what usually they use, and that's what we're going to look at. So we're going to use a logistic curve for g. So when we use a logistic curve, which is this kind of curve, I explain a little bit about, well here, it says, what's so good about logistic curves? They're good because its practical value arises from the fact that it has a squashing effect on very small or very large values, but it's almost linear in the range between 0.1 and 0.9. What does that mean? First of all, what do they mean by a squashing effect? They mean if you get really large values for x, what's it going to be? Let's say the maximum value here is 1. Even if I get notice that it doesn't actually ever reach 1. What's the idea here, whether the drawing shows that or not? It never actually gets to 1. But if I go way over here, what's it going to be very, very close to? What's the height of this curve going to be very, very close to? It's going to be 1, right? So even though I get a really big number for x, I only get a tiny little change in the height, right? So that's what it means by squashing effect on very large numbers. It doesn't make much change in the y value when you have even for a very large number. If you increment from this number to a much bigger number, you get virtually no change. And that sometimes is kind of beneficial. Anyway, that's the property of it, whether it's beneficial or not. But sometimes it is beneficial. Okay? So, and the same thing with very small ones, the same idea. So that's why it turns out to be useful. Anyway, g just has to be monotonic, and this curve definitely is monotonic. It's always increasing. Okay, so it is monotonic. Okay, so here it is. No, here it is, the nasty thing. This thing. Okay, it looks pretty nasty but where's g? Here's g, right? And what are we putting into g? Forget about this theta, just ignore it. So what are we putting into g? It's that sum that we've been talking about, right? That's what we're putting into g. Now what does g actually look like? I forgot to put g. But the g function looks like this. G is this. This is the definition for a logistic curve. It's 1 plus e to the minus, wait, is it minus? Yeah, e to the minus x. That's the definition of g. In other words, if I graph that blue curve there, I'm going to get a curve that looks like this. Okay, I'm going to get that curve. Okay? And what I'm going to do is I'm going to put in G, I'm going to put that calculation that we did, that sigma. So I'm going to write not g of x like this, but g of that sigma stuff. Right? G of that sigma stuff, right? The whole sigma. What did we have? In our case, it was what? xi, wi, j. Okay, so that is going to, and I left out the theta thing. I left out this plus theta because we really don't need that. Plus theta. Okay, we don't need that. So it's just g of that. Now remember, this produces a number, right? So I'm putting a number into g. I'm putting a number into here. That's not such a horrible thing to do, right? Like I might put 3 in here, so I would get what? 1 over 1 plus e to the minus 3. Well, that, I can figure that out on a calculator. And it's going to give me some number as a result. And that is the output for this node. So the input, we already figured out, it's the sigma stuff. Okay, that's the input. Now what does it send out? We put the input into the g function, and that's what comes out of it. So that gets sent out to here. Okay? You understand? All right? So that's what gets output from this node. Let me try and make this picture a little cleaner. We had 2 nodes here. We have 3 nodes here. 1, 2, 3, 4, 5. 1, they both go to 3, and then they both go to 4, and they both go to 5. But let's just focus on what's going to 3. So what's going to 3 is we're going to take, what was this called? W sub what? 1, 3. And what's this called? W sub 2, 3. And this we called x1, and this we called x2. Or maybe, sorry, this is x1, this is x2. Okay? So what goes into this node? x1 times w13 plus x2 times w23, right? And that can be written, we said, as xi wi3. Right? Can be written like that. So that's what goes in here. We just said that goes in here, but we can rewrite it like that if you want. And then the question is, what comes out? We take what goes in and we put that into G. So we put that into here. Okay? And that's what I have here. I'm taking that and putting it into G. And if I put this into G, it means I have to put all this where x goes. So I have to put it up here. This is where x goes, right? This is, x is up here. I have to put all that up there. Right? And so we get that there. Right? And that is the output. And if you follow that, you're 80% of the way to understanding neural network. Okay? So, so that's what comes out of that node. Okay? So it looks like a big mess, and as I said, we don't really have to think about it too much. All right, now, going back to our example, what time is it now? Time to go, okay. All right, so we'll leave it at that. And so what am I going to come back with? Where am I going to start on the next lecture? Well, obviously right here, but I'm going to review what? I'm going to review this, right? I'm going to say, what is the output here? Right? And what am I going to say? I'm going to say that is the output for here, right? Okay? And then we know what the output is for here. And that's basically what we need to know. And sorry, there's one more part that we're going to need to know. And that is, how does the network learn? How does it learn from its mistakes? Okay? Because it's going to go through, it's going to make a prediction, and then it's going to correct itself based on the fact that there was some error. And it's going to fix things up. And the way what it's going to do to fix things up is it's going to say, oh, there was some error at the end. Like I predicted it was going to be a 6, and it was actually an 8 or something. That's what I predicted would come out. Like I predicted this person is going to earn $8,000, and they actually earned 10,000. So I made a mistake. So I made a mistake of $2,000 in my prediction. So now I want to change what's here somehow according to that $2,000. And what we end up changing is these W's somehow. So that then the calculation will be different when we do it again. And somehow we have to figure out how to change these W's based on the 2000 error. And that's called learning. And the network will learn and then get better and better. So you keep sending more cases through it. It learns more and more and more. The W's change over time. And then and you might be confused, like, wait a second. How did we know what the W's were at the beginning? So the thing is, you set them at random at the beginning. So that sounds crazy, but that's the way it works. You set them at random, then you run the data through, it makes a mistake, causes you to change the W's, then you run new data, another data set through, it makes some smaller mistake hopefully, then you change the W's again, and you have this algorithm for how to change the W's, and you keep running more data and more data and more data, it learns. What does it mean to learn? It means it changes the W's, and finally you end up with something that works 98% of the time. Right? That's the way this works. Okay? So that's where we have to explain how it learns. And that's called, by the way, I'll just tell you, it's called backward propagation. Back propagation. And what it means is we're going backwards and up and changing the W's. Based on the error that we got here, we're changing the W's. Okay, that's all. Now for homework, I will give you this PowerPoint, and I might give you some quiz on what's in here, just from up to what we did. Just basically that you understand the W notation, and that you understand that this thing. I want to make sure that you understand, forget about the theta, but this part here. Okay, I just want to, you know that this tells you what's going into a node, and tells you and how to read this, what these mean. Okay, that's what I'll give you a quiz on next time. Okay, I just want you to understand this part right up to here. That. Okay? So that means what? Once again, just to review. This means this is calculating what's going into which node? The jth node. So if this was going into this j would be 3. Okay, if we were figuring out what went into here, this j would be 4. Okay, so this is calculating what's going into the jth node, and the p means how many of downstream, what's it called, downstream or upstream? Upstream. How many upstream nodes it's reading from. So here, this node is reading from how many upstream nodes? This one and this one, right? It gets input from here and from here. So it's just 2 nodes, so this P would be 2. Okay? All right, I'll post this video also, although there's a lot of space in between, so you'd have to hunt and find what I said. But anyway, I'll post it, and I'll give you this PowerPoint as well. And basically, I just want you to understand this, and that this tells us what goes into here. You don't even have to understand the G function. Okay, I'll do that later, but at least I want you to understand this. Okay? Okay, that's all.